Hi, my name is Guangyu Li, and the title of my project is um, Optimal Clustering and the Recommendation Method for Social Network. And this is actually an option 2 project, which means that I will develop a numerical algorithm-based software package for an optimization problem. Also, I'm working on my own, and the team member is just me. And this is outline of my presentation. First of all, I'm going to talk about what kind of optimal recommendation is going to be done in which kind of social network, and why we're going to do this, and how the optimal graph clustering method is going to help to improve the recommendation. And next, I'm gonna talk about the mathematical formulation of this problem and which kind of method we're going to use to get the solutions. And finally, I will present how the experiments and the results are get, and I will give some analysis and conclusions at last. Okay, let's first introduce the social network, which are called event-based social networks. Event-based social network is a kind of network which gets people together in some offline events, like hiking, football, or dating events, where people are required to show up in the events in person, and they can build their social networks based on these events. So for now, several websites like meetup.com, plancast.com, and eventbrite.com provide such service. But unlike online social networks such as Facebook or Twitter, offline social networks is supposed to be more cohesive since users are going to meet each other face to face and have stronger interactions. Actually, those websites are trying to improve their performance of recommendation because they can actually profit from the tickets of the events, and the number of tickets itself is actually related to the recommendation performance of the algorithms. Also, in some previous research, some researchers found that if we correctly identify the communities among other users, performance of the recommendation algorithm can actually be improved by recommending events to the user within the same community. So, intuitively speaking, if we know who your friend is, um, it's a lot easier to recommend events for you. Thus, how to detect user communities or how to cluster a social network becomes a critical solution, critical question. So, formally speaking, this project contains two optimization tasks, and the definitions are as follows. The task 1 is that given a social graph G with E, where V represents the vertices in this graph and E represents the edges in this graph, and the weighted matrix W and the integer K, which is larger or equal to 2, cut the social graph into K subgraphs such that the sum of the weights between two different communities is minimized. The weight matrix W is the social bond between the users, and there are several ways we can define it. For example, the number of common events, the number of common groups, and so on. And the second task is that given the communities we get in previous problem, and given loss function, how we can find the optimal similarity matrix that the loss function is minimized. The similarity matrix is the influence put on by one user to another user, and given this matrix, we can calculate the score of the events to each of the users, and according to the score's rank, we can recommend the events to the users. Okay, before we talk about the clustering method, let's first talk about the social network construction. Actually, using all this information across on the website of the meetup, we can know all the users who attend in each specific events, and so we can use the users as the nodes in this social graph, and we can define the edges to be the co-appearance in at least one event. For example, the two users A and B, if they both appeared in the same events, then there is existing an edge between the two users. And we can also define the edge's weight using the number of co-appearances in all of the events in the time slot. For example, uh, uh, in last year, user A and B both attend um, the same event list of two events, event A, event 1 and event 2, then the co-appearance number is just 2, and we use 2 as the address weight between the two users. Okay, given this graph we constructed previously, we can use the clustering method, which is called Fedor's approach. And actually, I'm following the paper whose title is The Property of Eigenvectors of Non-Negative Symmetric Matrix, and its application to graph theory, which is written by Fedor and published in 1975. The core idea is to use matrix theory and linear algebra to study the properties of the weight matrix W and the Laplacian matrix D minus W of the graph, and relate it back to various properties of the original graph. According to Fedor's approach, actually, the optimization problem is just as the equation as follows. So let A denote the weight matrix of a network. According to Fedor's approach, equation 1 is applied as a graph partition objective function and each binary card for each binary card. And D is a diagonal matrix in which each diagonal value is the sum of the corresponding row. And L is the Laplacian matrix, which equals to D minus A. And Y is a column vector, which can only take two values. If yi equals to 1, which means that node I are clustered into one cluster, and if yi equals to minus b, means that node I should be clustered into another cluster. So in order to implement the algorithm, we actually use programming to build the algorithm. So the program's input is actually the G as a graph and the number of cluster K. And the output is the user cluster set C, which consists of C1, C2, and so on. So the core idea is just to binary card all of the existing cluster into 2, and until we reach the final cluster number K. Actually, the most difficult part of this algorithm is just the binary card part. The algorithm for binary card consists of following steps. So the first step is to calculate the weight matrix of each cluster using the information we get. And second step is to solve the equation as follows for eigenvectors with the smallest eigenvalues. And third step is to use the eigenvectors with the same second smallest eigenvalues to bipartition the graph. And the final step is just to decide if the current partition should be subdivided and recursively repartition the segmented parts if necessary. Okay, next I'm gonna talk about the method for recommendation, which is called cluster-based collaborative filtering. Actually, pure collaborative filtering is actually a very widely used method in a recommender system. Um, the core idea of this CF method is first to calculate the similarity between each user pair, and actually we use cosine similarity. For example, if we have two users, A and B, and the user A has attended a lot of events, and these events actually consist uh, events vector, and the value of each event should be taken 1 if A actually attended that event, or 0 the otherwise, and the same with B. So if we want to calculate the similarity between user A and user B, we actually uh, using the product uh, of the two vectors divided by the two norms of these vectors. And also for one user I, predict the score user I gives event T using the weighted average score calculated by the following equation. So it turns out actually we can improve this collaborative filtering by only consider uh, the user I's neighbors who only belongs to the same cluster with user I. And also we can take in another tunable parameter W to decide how much weight to assign to each user J's score. So we call this improved recommendation method as a cluster-based collaborative filtering method. And we actually add the Wj to the equation mentioned before. And we also can create a loss function, which is as following. And Rj in this equation is actually the real score, which can only take two values appearing in a single event equals to 1 or 0 otherwise. And the second term is actually a regularization term whose purpose is just to keep this model from overfitting. So the problem is actually transformed to finding a set of optimal parameters W1, W2, and so on, such that the loss function equation 2 is minimized. Since it's actually easy to check that this form of problem is convex problem, and so it actually can be solved by just calculating the analytical solution. Or we can use a numerical method, which is called a stochastic gradient descent, to find the approximate solution. Here we use the second option due to the easier implementation. Stochastic gradient descent, instead of using other examples to update for each iteration, stochastic gradient descent randomly use only one example to update the parameters in each iteration. The original gradient Q thus is approximated by gradient at a single example, which is as follows. Okay, so next I'm gonna introduce my experiment and the data set I crawled and used. The dataset is just crawled from meetup.com using Meetup's API, and the statistics are about 10,000 groups and 1 million users from 2002 to 2014, and about 8 million RSVPs. And actually, we use MySQL database to store all this information. And since it's a very large data set, we're going to use only a subset of this data set to run the experiment. And the subset actually consists only New York's events and users. And we build these algorithms using Python and store the data using MySQL. Okay, so in order to show that different cluster number k is an influential parameter, we actually run this algorithm several times to find the optimal value of k. So we got this results for clustering value k. We found that if k equals to about 10,000, the objective value achieves at the minimum, which is 2.53. So in next stage, we are going to use this cluster to give a recommendation. And then for the recognition evaluation, we use the parameter recall to evaluate our recommendation performance. The recall value is actually computed by the number of users we predict rightly, divided by the number of predictions we give. So we can see that by introducing the concept of cluster and parameter similarity parameter, the recall value is promoted by nearly 10% compared to the pure collaborative filtering method. That's all the results and conclusions. Thank you.